Hello and welcome to the Sirovision webinar. On the screen you'll see the basic outline of what we'll go through today for Sirovision. We'll start off with a quick introduction to Sirovision, what it is and who uses it and why. Then we'll look at how we create 3D images from field photographs, how we use survey control, and how we actually georeference the 3D models that are generated in Sirovision. Then I want to spend most of the time today going through the geological and geotechnical mapping and analysis functionality in Sirovision 5.1 and spend some time on the new slope stability analysis tool for the automatic detection of wedges. And then just finish up with let you know what's on the roadmap for Sirovision over the next year or so. So what is Sirovision? Sirovision is a photogrammetric remote data acquisition system. Basically, you take a left and right photograph of a rock face, and the software will generate spatially accurate 3D images from those left and right photographs, like the image that you can see in front of you here. Once we have the spatially accurate and georeferenced 3D image, we can map structure on that 3D image. We can map traces and planes. When you map that structure, you get immediate geotechnical parameters output from the software. Once you've mapped your structures on the 3D image or a mosaic, we can then use the analysis tools in Sirovision to analyze those structures. Sirovision includes basic analysis tools such as stereo plots and rose plots, but also some other more advanced tools such as the slope stability analysis tools. We'll cover these in more detail as we move through the webinar. As mentioned, the slope stability analysis tool is a new tool which has been added in version 5.1, and it enables us to input domain characteristics onto a 3D mosaic, such as rock density, cohesion, pore pressure, and angle of internal friction. And the software will basically automatically detect wedges and visualize those for us on the 3D image, where we can see the actual mass and volume and size of those wedges. Again, we'll cover that in more detail later in the webinar. The software then allows us to export our data. The two types of data that can be exported are the 3D image files, which include wireframes, point clouds, decimated mesh. These can be exported as Sirotiff format or DXF format. And the second thing that can be exported is the discontinuity set data, or the digitally mapped structural data. And that can be exported separately to a lot of standard file formats such as Datamine Studio, DM file, DXF into Vulkan, DIPS format, Surpac STR files, and we're adding a list of other commonly used formats to the software with the next release 5.2. Okay, so that's basically in a nutshell what Sirovision does. The main users out there predominantly are geotechnical engineers. Use it for geotechnical mapping, detection of wedges, fracture frequency analysis. Geologists for geological mapping, mapping lithology and mineralogy, and to a lesser extent surveyors, and in the future mining engineers. Future releases of Sirovision will include blast design fragmentation analysis and also some tools to calculate overbreak and underbreak volumes. Say that's in the future, but predominantly the users out there are geotechnical engineers and geologists. Okay, so fieldwork and equipment. How does it work in the open pit? What you do is you take left and right photographs of the same rock face, basically. There's three basic rules. It's very easy, it's very quick. You take the adjacent stereo pairs must have about 30% overlap, and the distance between the cameras has to be at about a ratio of 1:7. If you follow those three rules, the photography is very easy and very quick. Survey points that we require for the system, basically to georeference a mosaic of 3D images in Sirovision, we need 3 known control points distributed throughout that mosaic in a roughly triangular distribution. Now this can be a combination of, as you can see in the screen here, 3 control points placed on the rock face itself, so 1, 2, 3, in a triangular shape, but it doesn't have to be a perfect triangle, but just in a roughly triangular shape. Second example here is a 3D mosaic. We have a single control point on the rock face, and we have surveyed in a left and right camera position. Again, we get our 3 control points. Once we know that, we can georeference this entire mosaic. Third example, and this particularly relates to the use of GPS or geotaggers, where we can use 3 camera positions to georeference an entire rock wall. We do that by, an example, if we have a geotagger attached to our camera, we take a photograph from point 1, point 2 and point 3. We build a mosaic, and then we use the GPS data from these 3 points to georeference the entire rock wall. It's that simple. And the newest build of Sirovision will include an automated process where it will read geotag GPS information from the metadata of the images and use that to automatically georeference a 3D mosaic. So this segues onto this slide, which is geotaggers and GPS. This, as I mentioned, is something new that we are adding into version 5.2, due for release early 2014, and that is the use of geotaggers such as the Solmeta or Nikon geotaggers, and also allows the use of recently released cameras from Nikon, such as the D5300. What these cameras do means we can take these photographs handheld, and the geotaggers will write the GPS data directly into the metadata of the photographs, which, as I mentioned, allows us to build a fully georeferenced mosaic straight from these photographs. What that means is that we no longer need external survey support. So particularly for consultants, you're self-sufficient. You use a geotagger, you don't need external survey support. So apart from that, for open pit, all equipment that you need is an off-the-shelf digital SLR camera, like a Nikon D7000 or a Canon. Fixed focal length lenses, but you can't use zoom lenses. Other standard equipment you need is a laser rangefinder, a carry bag, and possibly a tripod or a geared head, depending on what survey methods you elect to use or able to use at your mine. So that's basically it. Our equipment setup can be as low as $2,000, and as I say, it's a standard camera you buy in any camera shop, so easy and quick, cheap setup. So that was open pit, so I'll just quickly explain our underground system. We are quite unique in that we've developed a specialized CAE stereo camera, which is designed to take stereo photographs underground with one touch of a button. The idea of this is to allow you to take stereo photographs of a heading in basically a few minutes. For a single heading, you might take 4 to 6 stereo photographs, and you can accomplish that in 60 seconds or 2 minutes. So this unit, as you can see here, has been designed to be used by one person. It's self-contained. It contains its own lighting system, its own laser light system, and it's built for speed. So as I say, you can take the photographs for a single heading in a couple of minutes. So what do you use underground 3D images for with Sirovision? You can map geological boundaries, you can map mineral vein boundaries and calculate mineral vein volumes. You can gain an accurate location of rock mass features. You can use Sirovision 3D models for ground support and development QC, for contract supervision. And the benefits of this is that, like I say, you can capture this data in a couple of minutes, and it will give you a permanent digital historical record of rock mass as you mine. This image here is a mine plan with 5 3D images taken at different times as this heading has been mined back. And if I just click the next screen, this is through the other side where you can see the reef travelling here. So it gives you a digital record of, especially accurate digital record of the underground headings as it's mined. Okay, so that's a quick overview of the open pit and underground equipment required to capture stereo photographs for Sirovision. So what I want to go through now is the actual software itself, how you map, structure, what analysis tools we have in here, and how we can export that data out of Sirovision. And we'll also talk about the new Wedge analysis functionality. So this is an example of a open pit 3D image. Obviously, this was taken with a 24mm lens from about 50 meters, and just to show you the kind of quality that we can get with photogrammetry. The beauty of photogrammetry is that you can change lenses. It's very flexible. You can get into any areas in the pit, so you can basically map everything in the pit using a photogrammetry system like Sirovision. And this is the kind of detail that you're getting with that kind of lens, with a Nikon 24mm lens. So you can see that it's pretty detailed. It can be as detailed as you actually require the system to be. So in this case, we've got a single 3D image. Our basic mapping tools we can map traces or strings and planes. And basically, to map a string or trace, just press F3 and you can just map along a fault boundary or linear feature, like so. And when you map that, you can just left click on it here. In our property view window over here, it will display the geotechnical characteristics for that string. So we have dip angle, dip direction, persistence, centroids, etc. So basically, as soon as you map a structure, you have the geotechnical characteristics displayed and calculated automatically. I'll just map a plane. Just zoom out a little bit. So I'll map a plane. To do that, you just click around the boundary of the plane and right click to close that off. Now I've just mapped that plane, so as soon as I map it, click on it, again I've got the dip angle, dip direction, persistence and various other attributes that belong to that plane. And you might notice as we map a string or a plane that they're populated onto the stereo plot window here as we map. So basically you're just going to work through your 3D surface and map strings and planes depending on what kind of functions you want to perform. Okay, so we've mapped a string and a plane so far in our 3D image. We do have an automated mapping tool which is called the Fine Planes tool, and what that will do is we can set a minimum and maximum plane area size here in the property box. In this case I've got a 0.1 minimum to 15 square meters maximum, and we can also set a roughness an orientation threshold for the planes that we're interested in mapping. So when I set that criteria, if I run this Fine Planes tool, it will just run through the whole image and it will map every plane that suits that criteria, and you have an option to accept them or to reject them. So that's an automated or a quicker way of mapping across models. Other objects that you can map in Sirovision, probably less useful, but there's survey point and survey line. So if I want the XYZ of a survey point, I just plot that, it gives me the XYZ. Plot a survey line, I just want to know what the width of this area here is, plot that line, it would give me an end-to-end length and the coordinates of that survey line. Okay, another tool which is useful is the ability to plot a scan line. So if I just left click on the add scan line tool, then I left click where I want the scan line to start and where I want it to finish, it will draw the scan line and a sensor box. Now I can control the size of that sensor box. In this case this is it's quite a small scale image, and this particular box is 20 meters tall, so I might want to reduce that down to 1 or 2 meters, and do likewise for the height below 1. So this is I can adjust the size of the sensor box in meters, and the sensor line runs across here. So the software is set up to report on any structures which cross the sensor line, and from that you can actually work out fracture spacing and fracture frequency. Okay, so that's scan lines. What we'll do now is I'll open up another image where I've mapped a lot of structures, maybe about 50 structures, and we can then have a look at the analysis tools we have in Sirovision. So I'll just open that. As I said, this is a pre-mapped 3D model prepared earlier. We have about 50 structures mapped on here. So the next thing I want to show you is the Mapping Explorer tab. What this is for is this lists all the objects, the digital objects that you've got mapped on your 3D image. So in this case, I've got everything. I've got survey points and lines, strings, planes, and scan lines. So Mapping Explorer just basically lists all those objects. As I click on the node here, it will list in tabular form all the structures that I've got mapped here. So I've got all my geotechnical parameters listed for each structure that I've mapped, which includes dip direction, centroids, etc. One tool that we have in Sirovision is a schema wizard, which will allow you to add your own attributes to structures as you map them in the software. So in this case, it's as simple that you just build your own schema where you enter a value. In this case, I've got bench number, and I've defined that as a numerical value, and lithology, I've defined that as a drop-down list, so I can have a list of any types of lithology I want to use. So to put in sandstone, limestone, shale, example, any number of values I want, and so on. So I can add whatever data I want to the structures that I map. That's my training schema, so I select to use my training schema, apply OK, apply, and that will add the columns for the custom data that I've just defined. So here I've got my map structures, but I've now got my drop-down list of lithology, so I can make that limestone, I can make this one shale, etc. So basically it just gives you complete control over what data you add to your structures. If I go back to the image view and I click on a particular structure, in the properties, there's a section here on custom data. So I've got my bench number, lithology, ore type, that type of thing, my custom data, which can be edited from here also. So as I say, the idea of that is to give you complete control over what data you add to your structures as you map them. The reason why that is relevant is we move into the next tab, which is the Analysis Explorer. This is where we will build analysis sets, which I've got one built here already. So let's just delete that and we'll begin again. We'll start with a brand new analysis set. So just delete. So create analysis set. So what I've got here, I've got all the parent data, all the structures that I've mapped on my 3D image or 3D mosaic. And what I can do is create a filter, and this is kind of like a basic SQL query filter where you can just pick out values and build a query. So in this case, I just click on plus, and this is where our custom data is relevant, because I can build a query based on the standard parameters such as dip angle, dip direction, etc. But I can also use the custom data that I've added. So it basically gives me complete control over what analysis sets I can actually work with and build here. So in this case, I just want to pick out everything which is on bench number 0 in this case, and give me everything with a dip angle which is greater than 40 degrees. So you can build as big an equation as you want and pull out whatever data you like. So let's apply that. That's pulled out most of the data. So this is a set, and here's the criteria I used to build that set. So create that set. So now I've got my filtered set listed here, and again in tabular form. I have all the data attached to those structures. To look at our orientation sets, we have the stereo plots here, which I'll just make a little bit bigger so you can see that. I might want to apply contouring here to try and work out how many orientation sets I'm going to have on my data, so I'll just turn on the contours. A lot of this functionality is kind of stereo plot analysis that you'll have in dips. The advantage, of course, in Sirovision is that whatever you look at on the stereo plot, you can see the physical equivalents in the real world on your scale georeference 3D image. So you're dealing with orientations here, and here you're dealing with actual physical sizes and physical location of what you're analyzing. So to build orientation sets with the data that we have here, we probably have two dominant orientations of structures here. So we just select the Create Clusters tool, create that. You can input the number of orientation sets that you want to work with. You can elect to remove any outliers and set a maximum degrees the difference between the outliers and the rest of the structures in the set. Hit OK, and then we'll just automatically build our orientation sets here. So in this case, we've got a red and green orientation set. As you see in the stereo plot, we've got the main plane, and the mean vector is the square icon here, and the poles, so the rest of the structures in that orientation set. If I jump back to the 3D image file, I can see my two orientation sets here are my red and green orientation sets. So that's how quick and easy it is. If I want to define another orientation set, basically click the Define Orientation Set, just place the mouse on the stereo plot, click and drag the ellipse, and build another orientation set. So now I've got three orientation sets to work with. As I click on each one, I've got the structures themselves. If I click on the orientation sets parent node here, I've got some statistics on those sets, like Fisher K values and average dip direction. So it's that easy. We've got our orientation sets. Just to mention that we have all the other standard tools such as rose plots, etc. I'll just turn that off again just to tie up the display. We have some statistical histogram functionality here. We mentioned before we have set spacing histogram, so if I click on that, that will give me a kind of bar graph output on the average spacing of the structures in that particular orientation set. Same thing for persistence distribution within that orientation set. There's another range of histograms and other tools in the software. We can also look at data on the custom attributes that we've attached to our data. So in this case, we added lithology as a custom data, so I can pull up some charts, just basically giving me bar graphs or pie charts on the lithology of my structures here, that kind of thing. So just to help with your geological reports. So that's how we build our orientation sets. This leads into what we want to spend time on, which is the wedge analysis functionality in the software. So I'll just load up another image where we've got some more unstable wedges. This mine rock face has been mined pretty well, so there's no obvious wedges on this example. So I'll just open up my wedge example here. And this has some nice wedges in this image. So I'll just pin that open, bring that over a little bit, and just open up this 3D image. So this is one I mapped earlier again. Just pin that closed. You can see in this is a nice example because we have quite a wedge here right in the middle of the image, and some other areas here which looks pretty unstable. So to get back to how we work with analysis sets, and run the automated wedge detection tool. In this case, we've got a red and green orientation sets. Again, if I click on that and then move back to the image, you can see my red and green orientations, dominant orientations. So go back to the Analysis Explorer, and just what I do is, just to first explain. In the 3D image, what we've added in 5.1 is domain characteristics for this 3D image. So what we can do is go into the property view for this image and add geotechnical parameters such as pore pressure and rock density in this case. Now at the moment in the software we can add those domain geotechnical values to the whole 3D image. In the next build of Sirovision 5.2 we will adapt that so that we can map different domains across a single 3D image or a single 3D mosaic. So you can add different domain geotechnical parameters across different parts of a 3D image. But just at the moment we treat a single image as a single domain. So we can input pore pressure and rock density here. I go back to Analysis Explorer. What I want to do is get the software to tell me, is there any unstable wedges happening between these two orientation sets, these two dominant orientations of structures. So to run that, I just run the stability analysis tool, opens up this little box here, and it allows me to select what orientation sets I want to compare. In this case we've only got two, so we've got red and green, and again we have some other geotechnical parameters we can input into the software to contribute towards the definition of the wedge, or which will determine whether the wedge is unstable. So in this case we have cohesion values and friction values, which is a critical friction angle. As I said before, on the domain we have pore pressure and rock density also. So all of these values are taken into account by the software when it tries to calculate whether wedges exist and whether they're actually unstable or not. And those wedges, if detected, are given a classification. Other values in here you can edit is the persistence method. You can use local or use the maximum persistence of that set, or use the mean persistence. That is the persistence it applies to the two planes, which it will compare to see if they intersect to form a wedge. The last thing we input here is a factor safety threshold. So we can edit that value, and when it detects the intersection of two wedges, it detects whether basically the forces pressing down are a certain ratio over the forces holding the wedge up. I'm not a geotechnical engineer, you probably realised by now, but that's the way I understand it, that you can set this factor of safety threshold. So in this case I've set these values, set a factor safety threshold of 1.4. So I've created one of these already, so I'll not run that, I'll just come out of that. And when I hit OK, it will map a kinematic set, a new stability map. And as expected from looking at this 3D image, we've got, how many is that? 5 wedges. And here they are marked as a classification. So 3 of them are unstable and 2 of them are stable with friction. So it attempts to add a classification of how unstable those wedges are. The wedges are also reflected in the stereo plot here, the red lines being the planes of intersection and the yellow lines being the planes that intersect. So that is better visualized if we jump back to the image view and see what's going on. So as you can see, there's a lot of lines all over the place here, but say small image, we've got 5 wedges. So we'll just narrow this down for simplicity, and we'll select, I think, that one. Oh, pardon me. Let's go back. And we'll select the most relevant one, which is this one. Okay, so this wedge here, this nice wedge right in the middle of the image. What the software is showing us is that with the golden planes, these are the 2 planes that actually intersect. So As you flick around, you see this one's traveling this direction, and this one is traveling this direction. So you can see plainly how they intersect here. The red dotted line is the plane of intersection. So this is actually the direction that the plane is, that this wedge is going to drop out of the wall. It's actually traveling this way, downwards that way. So we've got the two planes intersect. We've got the plane of intersection, and we also have this blue tetrahedron. Now this blue tetrahedron is from what we can calculate the mass and volume of the detected wedge. Now this, the way we've set it up is we set it up for visualization, so you can easily see where the wedge extends to. And what we've done is I've set it so that if you're not sure how far up the wall the wedge actually extends, you can actually just click and drag on this release surface, which is the top of the wedge. This wedge may extend into the bench above or in the image above, whatever. So what we've done is allowed you to edit the release surface of that particular wedge. So if I grab that, I can just drag it up and actually extend that wedge, and that will recalculate the mass and volume of the wedge here, which we can see in the properties box. If I highlight that, click on that. In the properties box, we've got the mass and the volume of that wedge. So that is the use of this tool at the moment, is that when we detect wedges, we can see the mass, the volume, and the sliding vector that the wedge is going to come. So we know how big the wedge is, and we know which direction it's going to fall out of the wall. And as I say, you can edit the release surface of the wedge to allow you to calculate the mass and volume if you think that the wedge extends far above the image itself. So I've redrawn that again. The mass and volume is bigger. In this case, I think this wedge only extends down to about here, the top of the image, and that's how easy it is. It recalculates the wedge, and it gives me the new mass and volume of the wedge, both here in the properties. And if we go back to Math Analysis Explorer, I've got those values, mass and volume, dip angle, dip direction of that wedge. So basically, it's once you've detected the wedges, there's a lot of useful information that you can pull out of the software, and it's easy to simulate, to edit the wedge, to simulate if it's bigger or smaller than the software initially picks up. The other thing I just want to point out here with the tetrahedron, that sometimes it may look like the tetrahedron. Let me just make this bigger again to illustrate this point. I'll just drag it up here. The tetrahedron, if we look at the surface of the 3D image, the mass and volume of the wedge is calculated from the surface of the 3D image to behind the surface here. So to you it might look like it's calculating the volume from thin air, which is the front of the wedge, but the way the software works, it follows the surface of the 3D image, and it maps from the back of the surface of the 3D image to the tetrahedron behind. So the mass and volume is accurately calculated. Another thing is the software will only pick up daylighting wedges, so it will only obviously pick out anything that's daylighting on this particular surface. So that's the basic functionality of the wedge detection tool. You basically build your orientation sets. You input your domain characteristics such as pore pressure and rock density, cohesion, friction angle, and factor of safety threshold, and you run the stability tool, and it will pick out every wedge that is formed according to those characteristics. As I said, in future releases of the software, this is going to be expanded a great deal, which I'll talk about next. But before talking about future development of this tool, just want to quickly show you the export capacity of Sirovision. I'll just load back to the previous image that we were working with, which is this one. We've set up Sirovision so that we can export our data, our 3D models and our map discontinuity data, including the Wedge data, to as many other main mining software packages out there, such as DIPS, Data Mine Studio, MapTech, Falcon, Surpack, Gems, Leapfrog, all the other packages. So we've tried to make that as easy as possible, just very quickly. We've got this export wizard, 3D, select what you want to export. So we generally export the 3D images or the mapped objects or the analysis sets. You can basically export everything. To export a 3D image, we can export that as a Siro TIFF or a DXF. Now, I've been talking to most product managers from other mining software companies, and they are putting in the capacity to import our Siro TIFFs straight into their software. So certainly Falcon, Surpack, talking to Leapfrog, various other people about exporting our data in there. We'll also add a decimated mesh export function with the next build, just so we can export smaller 3D images. We can export wireframes, point clouds, anything. Analysis sets. This allows you to export the analysis sets we were just working with, so I can export the orientation sets, the wedge sets that I've been working with. See here, if I click on orientation sets, I've got a list of various export formats. So we've tried to make Sirovision as compatible with other software packages out there in the market. So we're compatible with all the big software packages. Okay, so just to finish off, we'll go back to the last section, which will be, I'll just give you a little insight into the future developments coming up in Sirovision. There's a few major things coming up. The second part of our automated wedge detection work is coming up in early 2014. This will expand this wedge detection tool, or I should call it the slope stability analysis tool, a great deal. Well, the major things which will be developed will be that we will be able to apply multiple domains across single 3D images or mosaics. So I think I mentioned that before. We can map multiple domain areas inside a 3D mosaic. The new functionality will not just be restricted to wedges. It will detect any type of unstable ground on the image. So in doing that, we work with block geometry as opposed to just simple wedges. It will represent interactions of minor structures like joints with major structures like fault lines, and it will also allow us to analyze non-planar structures or curved faults. It will also enable us to detect the likelihood of toppling. So it's going to really expand in terms of being able to pick up any type of unstable ground, not just be limited to two discontinuity sets or to just picking up wedges. And it will also represent excavation, geological and geotechnical constraints. So basically, in a nutshell, by the time we finish this work, it will be the most advanced unstable ground detection tool on the market, we believe, and will give you the highest degree of certainty as to whether something is going to fail. So that is being worked on currently in conjunction with the CSIRO, and that will be ready for release next year, 2014. Something else we are putting into the software is we've recognized the fact that for both underground and open pit, we need to remove the need for external survey support. So for open pit, we are developing the use of geotaggers and GPS data being written straight into the photographs, kind of like your iPhone does right now. But in doing so, we will enable you to take photographs with a geotagger and then build automated 3D mosaics which are automatically georeferenced using the GPS data which is already written into the photographs. So again, this will remove the need for external survey support. So particularly for consultants, that will make you completely self-sufficient. And as I mentioned, we're also working on a method to do that underground. That's a little bit more tricky, but we are working on this definite possibility that we can get that completed by next year, mid-next year. One thing down on the pipeline, also in conjunction with the CSIRO, is we're going to add in some automated blast support tools. And the major one there will be fragmentation analysis, where we will be able to take 3D images from a draw point, and the software will automatically give you a size distribution of fragmentation. There'll also possibly be an overbreak and underbreak volume calculation tool added, and also a fly rock hazard tool, which will give you a hazard map, the likelihood of rocks flying off the rock face, which may cause a hazard. So there's a few blast support tools there which will aid in the design of your blasting patterns to improve blasting performance. So that is basically it. Just try to keep it to as close to 40 minutes as I could. So we've received some questions through the session, so we'll just answer those now. Thank you.